Hey guys, we are Team 2 here to present our Uganda vaccine plant project. BCG vaccine is used to against TB. It's highly infectious and can easily spread through the air. Every year, millions of people die of it. 90% of the deaths were in developing countries like Uganda, but only a few people have access to the vaccine. This vaccine plant will not only help healthcare in Uganda, but also manage to boost the local employment rate and improve people's standards of living. To reach this goal, we broke the project down to three parts. Firstly, choose a suitable location to build the vaccine plant, and then choose a proper site to design and build the dam together with the hydroelectric power station. Finally, design pylons to transfer electrical energy to the factory.
At the beginning, we do background research to find the most suitable location. For example, the distribution of water resources in Uganda, the medical conditions in Uganda, and the population concentration areas in Uganda. We found that the most popular city is Kampala, and the major lakes are Lake Victoria and Lake Albert, because labor, water, and transportation are important. So we decide to locate it in more developed cities, like Kampala, Jinja, or Mbarara. There are some examples. In the first one, there are many hospitals, restaurants, and houses around. It is near the lake and two departments of water solutions, but it is a little far from the airport. And the second one, there are many streets, hospitals, and factories around. It is near a river and is a cluster of industrial areas, and it is not far from the airport as well as the bustling city center.
All of the options are quite nice. So to make the selection process more measurable, we created a criterion list and assigned weights for each one, from 1 to 5, based on how important it was to the operation of our vaccine plant. With scores for each location clearly shown, we could easily pick 3 with higher marks, location 1 and 2 in Kampala and 6 in Jinja. We didn't make many changes during the process, but did encounter a critical decision when choosing the final recommended site. We finally chose the site scoring 64.5 instead of the one scoring the highest. Let me talk you through why we made this decision. So based on the criterion list, option 1 and 6 differed at the closeness to a large population and security forces. Since the gap between the scores were quite small, we decided to take a closer look at each norm. When we assigned marks for each site, we only considered whether it complied with the criteria or not, but did not evaluate how well it conformed with the criteria. Both locations 1 and 6 had access to an adequate water source and had advanced infrastructures and excellent road networking in surrounding neighborhoods. But location 6 was near to a much bigger river and could gain security support from local barracks. Moreover, location 6 in Jinja was near to many entertainment places for workers and researchers.
So now we will talk about the numerical methods that we used when building our dam and designing our dam. So first, we used Bernoulli's equation to find the energy per unit mass. When doing this, we made the assumptions that first, it's incompressible. Second, it's inviscid, which basically means there's no shear force. And third, to ignore the change of internal energy. So the equation we found for energy per unit mass is theta is equal to P over rho, which is V squared over 2 plus GZ. We then use this to find the element of upper and lower stream of the dam. And then the energy difference per unit mass allows us to find the energy available to the generator, which is 6.7 megawatts, for which the dam needs to be 50 meters tall. The location of the dam was then decided upon multiple factors like the span, to get a shorter span, transportation, and many more things. When actually selecting a dam, doing and doing the design, we looked through several possible structures. But then in the end, we decided to go for the arch dam design, as this is best suited for valleys, which is where we would be placing our dam. While doing our calculations, we also found certain key relationships, such as between the volume and the depth of the reservoir, and also between the depth of the reservoir and the discharge rate through the penstock, which can be shown by this equation. So in this, Q is discharge rate, and that's equal to velocity times area, and velocity can also be simplified into square root GH.
Now let's talk about the relationship between the depth and volume. We decided firstly to find this function that relates the area and depth, and then use integration to find the relationship between volume and depth. We used Google Earth to slice the reservoir into different slices, then document area of the reservoir at each depth. This process can be visualized by the following animation. Slices are separated in 5 meters intervals. They are also well approximated by the Google Earth inbuilt 3D measurement tool. We then plot data points as a scatter plot in Excel. A trend line with mathematical expression is determined and displayed. We are very satisfied with it as its R-square value is very close to 1. We then reversed the relationship in the previous slides, integrated, then reversed again to find the volume depth relationship. Again, we used Excel to find a decent approximated expression. Now it is the time to construct the model. We will first find the model describing how volume varies with time, then use the volume depth relationship to find how depth varies with time, and eventually how power varies with time. We used an iterative approach to model the change of the reservoir volume over days. On day X, there will be V volume water. On day X plus 1, delta V volume water is added to reservoir, which raises the depth of reservoir to a depth of H dash. Knowing the H dash following the relationship between discharge and depth, we can determine the volume water that will flow out of penstock on day X plus 1. Therefore, knowing how much water flow in and out, we can calculate net flow, hence determine how much volume water is stored inside the reservoir on day X plus 1. There is also a special case we need to consider. If water added exceeds the maximum volume of the reservoir, the excess amount of water will flow out through the spillway. This needs to be taken special consideration when building the model. Based on the two cases above, we constructed our model on MATLAB. Here's the result of how depth of reservoir varies time in each area of penstock. Knowing the depth means knowing the discharge through the penstock, hence knowing the power generated. We tried 4 different areas for the penstock, 0.1, 0.2, 0.3, and 0.4 meters squared. As the requirement states that minimum power generated should be no less than 2 MW, the only suitable area of penstock should be 0.3 meters squared. After gathering results from the mathematical modeling, the final parameters we decided are listed as follows, which have an area of penstock which is 0.3 meters squared, a penstock radius of 0.3 meters, and the type of turbine we chose for our dam is Francis, as it can achieve 90% efficiency in most time of the year. During the modeling process, we have made some critical changes. We changed the fundamental assumption. Our team's initial assumption is that the flow rate will be constant throughout the year, and started building the model around this assumption for an entire week. However, we then realized that it is far too unrealistic, so we changed to an assumption or a fixed area of penstock. This means varying flow rate, which increases the complexity of the model and requires the model to be smart in a way, as it needs to constantly switch through special cases. So that means also we need to apply if and else loops that must be used. So we changed to MATLAB instead from Excel.
Let's look at the pylon design. First, we designed 3 sketches based on hammers, banana trees, and peace signs. The banana tree is the national symbol of Uganda, and peace signs represent the good wishes of laboring people to struggle for life. Then we converted the design drawing into 2D pylon sketches and added the nodes and branches. We used bars instead of beams, since it can subject to axial forces alone. Then we modified the number of bars and nodes to satisfy the equation B plus R equals 2J. Because we found that the unknown forces on each node are no more than 2 in statically determinant condition, which are enough to solve the equations. But for B plus R is greater than 2J in statically indeterminate condition, we found more than 3 unknown forces existing equations, which are insoluble by hand calculation. To reduce the calculation error and the complexity, we changed the bottom angle from 87 degrees to 90 degrees. After typing the structure in GSA, it's lucky to find that the hand calculations by using method of joints are the same as the GSA calculations. Then we choose steel S235 as the material of the tubes and deduced the formula as shown on the screen. By assuming that the thickness is constant, we tried different radius to calculate I and A, and compared the products of I and A on bars, and those from assumptions. It's found that choosing 20 millimeters as radius is totally enough for all pressures in the construction. Then we made some changes in dimension conversion. Firstly, we added branches to balance the structure, since GSA mentioned us that our model cannot be run correctly. It's found that the X-shaped structure is more stable than the original one. If there are axial forces acting on it, the additional bar can cancel the forces acting on the opposite one, and we stressed the inside structure to decrease the deformation. We initially placed pin and roller in 2 sides, but we ignored that the situation allows the whole structure to twist, so we changed the positions of them. After that, we analyzed the influence of car impact and wind load to our pylons, and calculated the nodal forces under wind load condition. Obviously, the maximum pressure on the bar is only 20 newtons per millimeter square, which is much smaller than 200 newtons per millimeter squares. This proves that our pylon can withstand extreme conditions.
To conclude, although we have faced through multiple challenges, our team still delivers satisfactory results for people of Uganda to help with their sanitarian problem. During the process, we have come up with many creative ideas to overcome the problems and made appropriate engineering assumptions to dam location, water power station site, pylon structure, and most importantly, we have demonstrated our team can bravely make change when things don't go as expected. However, as a team, we need further solidify our team's working skills and fully utilize everyone's speciality, which can increase the efficiency of our work. In this way, everyone's strong suit can give play to exact points that can help us to make much better project. And last but not the least, we are proud of the project we made and everyone's hard working. Without any one of us, we are hard to finish this project from nothing to everything. Thank you.